many people ask. What is our notation is also a question worth asking. We've already seen there's many different notations for some of the things I'm going to talk about today. Integrability means many things to many different people, and today I'm going to concentrate on the idea of integrability as being low complexity. In other words, you have a process that you're iterating, you have some variable or variables involved, and basically you're building a rational function and you're getting miraculous cancellations in the numerator and denominator of this rational function, and you wouldn't expect this. And this is in a sense the idea behind algebraic entropy. And many people have shown or looked at the idea that systems that have vanishing entropy are special. And it turns out that these systems also end up being integrable according to many other definitions. So this is a good detector of integrability of other definitions. Many people have worked on this. Some are in the room. And if you like, before the dots, these are sort of maybe the mathematical physicists that have worked on this. But this is also, the whole idea of entropy has been a very important idea in mathematics for quite some time. And there's a lot of recent work, including this last preprint by Blank and Cantar that was just loaded on the 1st of July. So this is a very fertile area for research. Now, as shown by Claude and Yamo and others, integrable lattice equations also have slow growth of degrees heuristically. In other words, you see lots of cancellations, lots of magic cancellations you might not have expected. Can we prove that they have vanishing entropy? Well, we're not going to prove it today, but I do say in the title exact. So I'm going to give some strong suggestion that subject to an enabling conjecture we make, it can be proved. The next question I want to ask in the second part of the talk is, can you see slow growth over finite fields? There are many advantages to treating algebraic dynamical systems over finite fields. In terms of computer time, in terms of being a detector to find parameter values where sometimes a system is special, and so I want to go and talk about that as well. Okay, let me just remind you for maps, what is algebraic entropy? So imagine you have a rational map in an n-dimensional space. You write it in projective coordinates by adding this x naught, and then the map has this form where you have a series of homogeneous polynomials. You can then iterate this map, and then you can cancel common polynomial factors because you're working projectively. And therefore, the degree of the map and its iterates is well defined under this process. So if you let d sub k be the degree of the kth iterate of this projective map, the entropy is defined as this. Now, it can be shown that this limit exists, and it's also invariant under birational conjugacy, so it's a good invariant. And if epsilon is equal to 0, the growth of the degrees is polynomial. Now, this is often used as a test heuristically for integrable maps. I mean, this looks a little bit tautological, I must say, because no. It's, I would say it's sort of guided folklore. There's very little proof of this, actually. Oh, I see. Actually, no, this perhaps should be, it's not very accurate. If epsilon equals 0, it's sub-exponential, but I'm not necessarily sure that that means polynomial. Okay, yeah. It'll be, yeah, I'll show, this is what will happen today also for the lattice maps. So, as I said, very little is proved along these lines of the claim. And the question is, you know, what about lattice equations, partial difference equations? What progress can be made in that direction? So, here's the plan. We're going to study integrable lattice rules, e.g., like the ABS equations, and their perturbations. when we study the integrable lattice rule, we're going to conjecture what the GCD is at each vertex. In other words, the term that can be cancelled at each vertex. And this will provide us with a recursive formula for the actual degrees in the lattice. And this will turn out to be a linear partial difference equation with constant coefficients that guides the behavior of these actual degrees. And then subject to this conjecture, you can prove vanishing entropy for certain rules, including the ABS rules. And indeed, the growth will depend on what you put on the boundary, and I'll give you examples of polynomial growth in that case. And the last thing we say is, can you look for the signature of slow growth over finite fields? Because work in recent years in the area of arithmetic dynamics, which is the intersection of dynamical systems and number theory, has shown that you can often detect properties of dynamical systems by looking for signatures over finite fields. And moreover, the signature is largely impervious to the actual details of the system. It really just records if the system has a certain property. And so we want to ask, can the property of slow growth be seen over finite fields? All right, these are known to many people here. I just list some of the sort of lattice equations we're talking about. So we're talking about rules defined on a quad. And ultimately, I'm looking at a partial difference equation with what are known as corner boundary conditions. So this is an integer lattice. We're going to prescribe initial conditions on the corners, and we're going to use a quad rule to develop the rule inside that quadrant and calculate the values. And we can do that because, by definition, a quad rule tells you how to calculate this on a plaquette given these three values. So I'm just giving you a menagerie of some of the things that are well known. I don't list Q4 simply for brevity, and also because we know that the ABS list can be obtained from this Q5 of Claude's by choosing appropriate parameters. And moreover, a lot of work has concentrated on lattice maps that have particular symmetries, like D4 symmetry. As well as those, I want to consider some other equations like that don't fall into the ABS scheme, like MKDV and Sine-Gordon, and also equations like this, E16 and E25, where E just stands for equation. And these last two equations are in this inspiring paper by Claude and Yamo, where they asked, does factorization, or can factorization over a small part of this lattice, in particular on a 2x2 square, if you iterate the rule over 2x2 and notice that you get a factor here that is common to both polynomials that reside at this vertex, can that be sort of used to suggest vanishing entropy? And so a lot of the stuff I'm talking about today is sort of inspired by this paper, this idea. Okay, so in general, as I said, the setting is that we're looking at a multi-affine rule on this square or quad or plaquette, like I've just defined here. So this is ULM, this is UL plus 1M, this is ULM plus 1, and this is UL plus 1, M plus 1. And it's presumed that you can solve this, it's presumed that you can solve this uniquely for the top right vertex. We're going to introduce projective coordinates. So what's happening is that at every vertex, we are actually going to have two functions, an x and a z function. And these will be homogeneous polynomials of degree 3. Now, if you look at the structure of these f and g, if you start with the multi-affine rule here for q, then you'll find that these projective coordinates are homogeneous polynomials where each term includes exactly one projective coordinate from each of the remaining 3 vertices of the square. In other words, this is the sum of products of one of the terms, the x or the z, from each of these other vertices. Now, as I said, we want to make this a boundary value problem, and we also want to look at growth of degrees. So how are we going to do this? Well, we're going to put in initial conditions that are polynomials in some indeterminate w. So this is what we're going to put in here and here. These are all going to be functions of some indeterminate w. So I specify the x and z polynomials in w at each of these places, and therefore it follows that as I develop inside the lattice, each of these sites is going to consist of 2 polynomials in w, and we're interested in their degree. We restrict ourselves to integer coefficients in these rules for various reasons of simplicity. And so we're going to call GCD LM the GCD of these 2 polynomials in w at each vertex. So in other words, XLM can be written as the GCD and some reduced polynomial, and similarly for Z. And we introduce this notation. The DLM, if you like, is the ambient degree at each vertex. D bar LM is what you get when you cancel this term, so it's the bar degree. And GLM is the degree of what you cancelled. It's the degree of the GCD. And as I said, low complexity or 0 entropy is characterized by massive cancellations of high degree terms in the GCD here. Okay. Now, following Claude and others, a heuristic way to probe entropy would be to start iterating this procedure, calculate the reduced degrees that you see. This should be of XLM and ZLM at each vertex. Computationally, this gets very hard very quickly because of just the size of things. So you can typically do this, say, on an 8x8 lattice, sublattice. Now, you might then extract the diagonal entries because typically the growth is going to be maximal in the diagonal. If you assume they come from a generating function and do a Parde type approximate, you can think of fitting this with some univariate rational function and then find the asymptotics from the closest singularity of this rational function. And this methodology has been used a lot by Claude and others when the initial conditions are not given along the boundary, but instead they're given on some staircase in the lattice. So you have a staircase of initial conditions, again, each of these things being a function of some indeterminate, and then you evolve in sort of staircases. Now, in a sense, this is a one-dimensional evolution, and you would have a sequence of degrees that are just have one index. But we are going to actually look at the full problem with the corner boundary conditions, where we're looking at the degrees with both indices, and we're interested perhaps in growth in any direction in this lattice. We would like to know what is d bar Lm exactly throughout the lattice for a given rule. Now, as I said before, the key issue for algebraic entropy relates to figuring out the growth of what you're going to cancel, the GLM. And for maps, this idea has been used by Peter, who had some conjectures about the growth of a reduction of H1. So what's our approach? Our approach is to find an exact upper bound for the ambient degree, conjecture a lower bound for the GLM, and therefore give us an upper bound for the reduced degree and hence for the entropy. Okay. Now, simply from the nature of all of these rules I've described, you get some simple inferences on degree. So the degree at the top right is bounded by the sum of the other degrees of the vertices, and the GCD at the top right is certainly divided by the product of the GCDs at the other vertices. So you can get some simple relations. In fact, you can even get this relation, that the degree of the GCD is greater than or equal to 3 times GLM if you move one to the right and one to the left. So in other words, if you ever get a cancellation, you certainly are going to grow exponentially. But the question is, do you cancel as exponentially fast as your ambient degree is growing? Now, here's a table of this lattice, and at each vertex, I've just put the degree, and the initial conditions chosen here were along here. These are all arbitrary constants, so that explains the degree zeros here, the degree zeros, and we inject at the origin an affine function of this indeterminate w for both x and z at the origin. And this is the sort of ambient growth you see of the degree. Now, it turns out you can exactly figure out what is going on here. So if you consider the maximal case of this relation, which is this, given by the A's, this is a well-known recurrence. You can find a generating function for it, and you can look at the asymptotics. So these numbers, ALM, are well known. They're called the Delanoy numbers. And here's, this is known work. This is not our work, but it's just an observation that this sequence is well known. Here's the generating function for this bivariate. It's a bivariate sequence, so it's a generating function in x and y. And the question is, what's the sort of development, say, along the diagonal? And if you look along the diagonal, the generating function for this turns out to be not rational. It's 1 over the square root of this polynomial. Nevertheless, it's a nice problem in combinatorics and asymptotics to be able to figure out what is the diagonal asymptotics in a doubly indexed sequence, and you can work out that it looks like this, which tells you that the maximal entropy for the ambient degrees is given by this number here. Okay, so that's the ambient growth. We haven't cancelled anything yet. But now let me go back with the same initial conditions and show you what is the degree of what's being cancelled at every vertex. Yeah. And you can see that this is also exponential. Well, at least you can see it's very big. I don't know if you can see it's exponential. And this is what it is for one particular set of initial conditions, boundary conditions. This is where I change the boundary conditions to having a slightly different degree. I make them all affine in W, and again you see this big growth of GCDs. Okay, we want to develop a recurrence that explains that degree table for the GCDs. We use this simple fact, which just comes from the rule, and so we define what is the spontaneous GCD as the extra part of the GCD that you get at every vertex, different in addition to what you know you're inheriting simply from the rule. And the spontaneous GCD satisfies this relation here. And now if we go back, and instead of looking at what we're cancelling, we look at the spontaneous GCD at every vertex, we see that this is very ordered now. So this is telling you what is being manufactured at every vertex in terms of a degree that you can cancel above and beyond what you know you're inheriting from the other 3 sites on the plaquette. Now, there's various patterns and observations that become clear. In the interest of time, I'm going to skip that, but go to feeding in this idea from Yamo and Claude's paper, who found that for many integrable lattice equations, there is a common factor that emerges on a 2x2 plaquette. So in other words, take the rule, put arbitrary initial conditions here. They found that when you go to this vertex, which is 2 to the right and 2 above this vertex, then you find that you will often find a common factor there that is a factor in the arbitrary initial conditions that you put here. And so, for instance, for H1, this is what this looks like, and you see that it is a function of only of these two vertices. The vertex that is 2 to the right and 1 down, and the one that is 2 down and 1 to the left. So maybe I should have said 2 to the left there. Now, this creates an ongoing spontaneous GCD. And so this is the sort of mechanism that helps to drive this extra reduction in the GCD. And this common factor has this degree here, where these are the degrees that you have at these two vertices on a 2x2 plaquette. Anyway, to cut a long story short, armed with this information and the knowledge of this ALM, which can be calculated for a rule by just doing a 2x2 exercise on the rule, we conjecture that this recurrence will generate the GCD that is observed. So what we call an enabling conjecture, given arbitrary boundary conditions satisfying that the GCD is 1, in other words, there's no non-trivial GCD for LM less than or equal to 1, then we find that this recurrence generates the actual GCD that you find from experiment. So the degree of the GCD is provided by the degree of this. And we've tested this on many different equations, and it survives the test. So this leads to the following consequence. When the degree of ALM looks like this, and it's important that the 2 is there, then the degrees of the common factors of the GCD that you're cancelling satisfy this linear partial difference equation. So it's related to the ambient degree and also to the GCD at other vertices. And then if you recall that the actual degree, d bar, comes from looking at the difference of the ambient degree and the GCD, then 2 shifts of this taken away from this furnishes this linear partial difference equation with constant coefficients for the degree growth throughout the lattice. And now you can actually solve that recurrence introducing this. And so you get the following, that for the ABS equations, including Q5, and for various other equations that I've put up there, Sine-Gordon, MKdV, and some of the equations that were thought to be integrable from the work of Yamo and Claude, we find that if you put constant initial boundary conditions here and make this linear in W, then you get linear growth of d bar Lm. If you make your boundary conditions degree 1 polynomials in W, you get quadratic growth. If you raise the degree of the initial conditions in W, you get cubic growth of d bar Lm. Now, it was important here that the degree of the factor that you were getting rid of had the 2 here, because some of the equations in the paper of Claude and Yamo actually don't have the 2 here. They have a common factor, but if you like, the degree of the common factor on a 2x2 plaquette is not big enough. So the machinery is not reducing and cancelling enough of the degree. And in this case, you can also prove prove in inverted commas, because you can again find a recurrence relation for the GCD, you can prove this exponential growth of these reduced degrees. Yes. Exactly. It may happen, and in a sense, this is still, the question is out here. What happens as you go bigger and bigger? But if you like, the message here is that for these equations, this little 2x2 engine and what's happening on a 2x2 level is sufficient to prove that you have vanishing entropy. But it's not to say that there could be a 73 by 73 where you get something additional. So, yeah. Okay, now that's the first part of the talk, and I have 5 minutes left. So I knew this was a tragic thing when I talked about the first part and the second part of the talk, but let me just see what I can do. All the rules I put up were algebraic, so they make sense over any field, in particular a finite field. So why don't we go back to the problem where we had these polynomials at every vertex, but now we repeat our experiments over the finite field Fp, where p is a prime number. So in other words, we look mod p at the whole problem, and we drive the whole thing mod p. Then again, you can define polynomials at each vertex, mod p, and their GCD mod p. And you certainly know that the reduction of the GCD that we talked about previously divides this GCD mod p, but you may get more happening simply because of the chance of more cancellation mod p. This gives you a chance to go much further in the lattice. And the question is, what should we take as a measure of growth? Now, if you want to go much further in the lattice, it turns out that this is a good measure. So we count the number of common roots, mod p, of the two polynomials at the vertices. And maximally, of course, the number of these roots is bounded by p. Now, what are we losing here? We're disconnecting now from degree because a lot of these roots could have high multiplicity. But if you try to keep track of the multiplicity as well, you'll be crippled by the same thing that cripples you over z, and that is the enormous growth of this degree. So we had to sacrifice that, and we looked at the number of roots along the diagonal as our measure of integrability. And it turns out it's a good measure, but not of integrability. So here is the exercise of walking along the diagonal mod p for certain integrable rules and their perturbations. And we're counting the number of roots that you see as you move along the diagonal. And the thing I want to point out is that integrable rules, like these two curves on the left, or if you prefer, this is better data where you average the data. Integrable rules get roots. Much quicker than non-integrable rules. Yeah, I think this. Yes, sure, please. Yeah.
You know, in integrable equation discrete, there are different classes of equations which we can detect on the level of symmetry, for instance.
Yes.
Like ABS equations all have symmetries of length 3, etc. But there are equations like the Seike equation, Kusinesk equation, which have no symmetries of length 3 and they have symmetries of length 5 as a minimum.
Yes.
And well, we can expect some other situations. Whether it is detectable in your approach, I mean, that I would expect that if you have a small plaquette, you will not have a common factor for Kusinesk or.
Yes.
I never did this.
Yes.
You know.
So it is true. So for instance, two equations I'm not talking about are Lotka-Volterra and KdV. There the factorization is over 3 by 2 or 2 by 3. And Tzeka is 3 by 3 factorization.
I mean the Seike equation that Adler, you know.
Yes.
Recently.
It's a?
What
Yes.
What equation, nice, small, but or what you publish in physics we'll talking tomorrow, I believe. So
Yes.
these equations look very similar, very simple, but they don't have symmetry, short symmetry. I wonder how that will be reflected
Well,
in spontaneous.
what I may get to is this is included in the finite fields analysis, the de Sitter equation, and it has the signature, or this signature, of integrability. But I don't know about, I mean, basically the nice thing I think about finite fields is that anything you're testing algebraically, you can ask to look at it over a finite field, and that is often much quicker. I don't know if they will work for the symmetries. Okay. All right. Yeah. Where was I? Okay. All right. So let me cut to the chase. Yeah. So as I said, these are plots. Say, take this one of integrable rules, Q1 and Q2, plotting the number of roots that you see mod P as you walk along the diagonal. And you see that Q1 and Q2 are the blue and red data here. So what happens? You don't have to walk very far. The prime is 127, and you're already saturated. You see the maximal roots you can see, number of roots you can see, P. If you perturb these rules, roots come much more slowly as you walk along the diagonal. Interestingly, they come. So this is interesting because the perturbations would have no GCD if you did this experiment like the first part of the talk, mod Z. There's no GCD at any side. But when you work mod P, you will start getting GCDs that are just a consequence of the fact that you have reduced to the finite field. Okay. Now, so there are various things that are different. Integrable things start much quicker at the bottom, and this is influenced by this factorization, because this factorization also starts giving you roots mod P. It's a mechanism for doing that. But they also saturate, climb much quicker, and they saturate much quicker. So
what is the value of P used for this experiment?
127. Yeah. So you can do experiments very quickly for reasonably large P. Anyway, it turns out that we can model both of these integrable and non-integrable cases with this simple assumption. Assume that a common root over Fp appears every t vertices as you move through the lattice. And then use the fact that over a finite field, a polynomial has on average one root, independent of its degree. Now, I highlight independent of its degree because now we've turned the whole thing on top of its head. Algebraic entropy is about looking for degrees. But this, over the finite field, is independent of degree. So now we're not actually monitoring degree anymore. What we're monitoring is factors. And if you end up at a vertex with one common factor, independent of its degree, it's going to contribute, on average, one root. Yeah. But nevertheless, because integrable rules have this GCD happening, and sometimes this GCD has two factors, then you're getting roots generated at each vertex much quicker than a non-integrable map, which is having to rely on a random process to generate common roots. So in this formulation, t equals 1 or a half is what you typically are going to see for an integrable map, and t equals p, order p is what you are going to see for a non-integrable map because you're relying on random generation of the roots. We have two models for this, and they explain the data very well. So for instance, this is a plot of saturation against p for integrable models. The model is the center curve, and it matches the data quite well. And for the case t equals 1, t equals a half. This is the case of non-integrable rules, and these are two bounding curves for t equals p and t equals p plus 1 and 2, and the data is well enclosed in them. And here is an overlay, similar to the picture I showed you before, of data and the predicted model curves in both of these cases. So this does seem to be a reliable way of detecting a difference in the factorization of lattice equations. Moreover, it appears that if you make a t-dependent scaling, and t is the one parameter in this problem, and t, remember, is the number of vertices it takes to see a root. If you make a t-dependent scaling, it appears that all of these curves can all be put onto one curve, 1 minus e to the minus x squared, which gives the proportion of the finite field that appear as roots of the scaled distance x as you walk along the diagonal. And this is a cumulative distribution function. It's very suggestive of some sort of underlying statistical Poisson type process. So as I said, this integral model is actually a test model for a number of common factors of these two things. And non-integrable equations can still produce the integrable signature over Fp if they have a factor, but it's not of high enough degree to give zero entropy, but it still gives a root mod p. Nevertheless, the difference in unscaled root curves can be used to test parametrized families of lattice equations over finite fields. This helps find the needle in the haystack, or as we've heard, integral systems are goldfish in ponds. And over a finite field, your parameter space is finite. So it actually is very quick to blow away the haystack or drain the pond in order to find the goldfish. And we've actually found some new lattice equations that are integrable via this method. Thank you very much for your patience.
One question.
Oh, well,
Only one question.
I can ask them later.
Okay. All right. Well, in view of the time, maybe, and we already had a little question session in between.
Yes.
We should move on to the next speaker. So let's thank John.